So now I'm back. Now you can see, right?
Yes, ครับ
Yay, sorry about that. So the problem was something like this, right? If I remember correctly.
yes ครับ
Okay, so here's the idea. So you're gonna assume, right, that k to the third less than or equal to 3 to the k for some k. And I gave you a hint that you will eventually need this. Okay. But then what you want to show, right, is that k plus 1 to the third is less than, which you don't know yet, 3 to the k plus 1. Okay, here's a hint. The hint here is expand the left-hand side. You're going to get k to the third plus 3k squared plus 3k plus 1, right? That's simple algebra, which you all can do it, right? And we want to compare it against the following, right? 3 to the k plus 1 is 3 to the k. Or you can write it as 3 to the k added together 3 times. Okay, so you want to compare these two. Okay, you know the following. I think at least this part, for those of you who get this far, know that at least these two guys are exactly these, right? So you know that the first part, that's clearly less than or equal to 3 to the k. Everyone get? Right? Everyone get? So here's the magic that you need to do. Here's the magic that you need to do. Show, this is a hint, this is a real hint. Show that this guy is also less than or equal to 3 to the k, and show that this guy is also less than or equal to 3 to the k. Okay, so if you know that these three guys, they are all less than 3 to the k, so that means the sum is less than or equal to 3 times 3 to the k plus 1, which is exactly the same thing as 3 times 3 to the k, which is exactly the same thing as 3 to the k plus 1. Okay, so that's one way to do it. There are other ways to do it, but this is one way to do it. You get the idea, right? So I think everyone got this far to compare the top two. Everyone got this far. But what you need to do is to show that these two guys are actually all less than or equal to 3 to the k, which you will need this. Okay? Any questions or any question? I think this is like the best hint I can give. Okay? Do some magic to show that this guy is less than that guy, and then you're done. K plus 1 to the third is all these, Peter. Are we good? Any questions or any questions? Okay. If not, any more question about the homework? Let's do hope. Don't worry, homework doesn't actually worth that much score, but you have fun as long as I remember. Hint for 10 and 9. What is 10 and 9? Pigeonhole thing. Right? 10 and 9 are pigeonhole thing. So you're digging. Okay, that's good. That's good. That's good. That's good. You have something. You have something higher to hope for than the score. Score is like the lowest. The lowest thing you could hope for. I love it. I love it. I love your attitude. Right. Let me tell you this: the grade and the score are the not the best measure of your ability. Is stupid. It's something stupid that the university forced me to do. If I were to open the school myself, there should be no grade. There should be no grade. Grade is stupid. Like you should separate the one who actually teach and the one who actually measure the abilities, right? When you combine the two, you get conflict of interest and a whole bunch of other things. Okay. Okay. So let's do this. Today, we're gonna do something actually. You're not gonna see that it's important now, but you're gonna see that it's very important in later the term when you do a whole bunch of things with Ajahn Kanat. Okay, what we want to learn today is called invariant, and the actual mechanism is called structural. How do I spell this? Structural induction. I think structural induction, I name it myself. So this is not official word. This is unofficial, or maybe someone use it like I do. Unofficial. Okay, something along that line. Okay. To make wrinkle. Okay, at least by now you probably think that you feel that you are a little bit smarter than you were at the beginning of the class. That okay, you know how to use logic and so on. You know what a proof is. That's like more than half of the population already, right? You know how to convince yourself, and you know how not to fool yourself. That's by now you should learn that. Okay, so let's learn the first thing. The first problem about invariant. So let me give you an example. Here's what I meant by invariant. If you have a checkerboard, right? If you have a checkerboard or chessboard or whatever, you know that a whole bunch of things, they are color, right? Red and black. Okay. A whole bunch of things, they're color red and black. Oops, sorry. And they do it like this. Okay. So, in chess, there is a thing called, I think called bishop, right? The bishop over here. They start in green, or maybe let's call the green black. Sorry about that. Let's start in white. So when I erase it, it's easier. So I don't need to do this. Okay. So the bishop in chess, they can do the following. They can go diagonally, right? They can go diagonally. And after they go diagonally, let's say they end up here. They can go diagonally again, right? And they can go diagonally again. That's a good, right? This is the go. Okay, this is the game, right? You can go diagonally, but you're gonna notice, right, that there are some places that you cannot land, right? There are some places that you cannot land. So for example, you can never land on the black ones, but we want to formalize that idea, right? The green patch, right? You cannot land on the green. Wait, I forgot one green. Wait 2 seconds. You actually can because I forgot this green. Okay, good. Now you cannot land on green. Or maybe you can. Oh, you still can. Okay, I'm good, right? So we want to formalize that idea. It's quite clear to everyone, but no, there's no way that you're gonna land on green because you start in white, and every time you do it, you only do it diagonally, right? So the question is, we want to say, can we land on green? And then we want to say no, but we want to say no mathematically. Like we actually want to prove that you can. That is a no. The answer is no, but we want to formalize that idea. Okay. So can anyone tell me why though? Can anyone tell me why? Right? Think about this. There are infinite number of moves, right? And what's wrong with my internet? Are you guys still here? Or did I lose the connection? Oh God, internet doesn't like me. 2 seconds. Blah blah blah. Okay, and there, and we now have a chat window. Okay, where did I lose you? Wait, let me. Did I record it? Is it recording? You are screen sharing, and it is recording. Okay. Okay, so the question here is, right, is whether you can land on green or not. And we want to formalize that exact idea. Okay, so can anyone tell me why exactly we cannot land on green? Why is it exactly? Given infinite number of tries, right? You can go all the way you like, right? You can go back here, go there, and go there, right? Given infinite number of turns, how did you show that you will never land on black? Because green is next to bishop. Because of diagonal. Good, right? Because of the way it moves, right? Because of the way it moves. But we need to quantify that. So let's make it more quantitative. Okay, let's make it more quantitative. So let's do this. Let's do this. So this is 0, 0, 1, 2, 3, 4, 5. So these are, let's call that the x-axis, and this is the y-axis. 1, 2, 3, 4, 5. What does it mean to land on green? What does it mean to land on green? What does it mean to land on green? Can anyone tell me? Okay, close enough. You meant the other way, but sure. Right, right. To land on green, that means the position, the bishop position, right? The bishop position has to be x and y such that x plus y is what? Anyone tell me? Is odd or even? Okay. This means it's land on white. It's even, right? So for example, you could just look at here. Right, 0 plus 2 is even. Odd for green. Odd for green, white for even. Good. So we want to show that no matter how you move, right? That means no matter how we move, this is what we want to show. How we move. If we start in white, we will end up in white. Okay. So that's good. Right? This is what we want to show. Okay. So this is your premise. Okay. This is essentially your, we're going to formalize this. This is sort of your invariant that x plus y is always even. Right? This is like your thing. No matter how you move, x plus y is always even. Okay. So let's do that formally. Right? So that means we're going to assume that it starts in white, right? Let's assume it's a proof. Let me write the theorem first. Theorem. The bishop is always in the white. Okay. So here's what we assume, right? Here's what we assume. So we're going to assume we start in white. In particular, what that means is that we start in white. So that means the starting point. Let me write this. The starting point is x and y such that x plus y is even. Okay. Everyone so far so good, right? We say that we assume that we start in white, but we want to be a little bit more quantitative, right? So we say that, okay, we start in x and y such that x plus y is even. I don't care where you start. Okay. We want to show that after one move, we still end up in white. Okay. So let me note something important about this statement. What I'm saying that this is important that we only show one move, that if you start in white, you end up exactly in the same state you're starting with, which is white, right? So that means even though we only show one move, we actually show infinite number of moves. Are we good? Right. Even though we only show one move, we actually prove the infinite number of moves. So essentially, here's what you're doing, right? So one move, you may have some choices. The graph is connected like this, right? Right. These are all the positions that you can, the state. These are all the states that you can end up in, right? If you show that one move, any move from that position, right? Any move from that position works. That means you're gonna get all the other ones as well, because after you land here, that move is still your move, right? So you show, oh God, that move is still, because you start in white, you're gonna end up in white. So that means if you show only one move, then you're done. Seven clear though. This is why it's called structural induction. That there's no actual order that you can order things, lay out things in like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? But all the moves are connected. The technical term is called a graph. But then if you show that all the moves that you can make, all the transition that you can make, gonna end you up in exactly the same condition that you started with, then you spread throughout the whole thing, the condition, the invariant. Seven good though. This is quite confusing. What? Okay, so what I am trying to say is the following, okay? That we will be showing only exactly one kind of move, okay? We will show exactly one kind of move, and this kind of move is the one as long as you start in white, right? So at the end, we're gonna have this theorem that you start in white. After one turn, we end in white. Okay, and then you may ask, Ajahn, what about two turns? What about two turns? Oh, two turns is easy because after you do one move, right? After you do one move, you end up in white. I don't care which white you end up in, but you end up in white. That means the second turn, that's the same theorem, right? The second turn is same theorem because you already start in white. You're going to end up in white. Is that good? Right? So the idea here is this guy and that guy are the same. So that means after one transition, you preserve some invariant. That means you start again at the step 0. Right? When you ask me, Ajahn, what happened about two turns? Because the first turn you end up exactly where you started. So that means you can do it next. This is more like graph traversal, more than recursion is graph traversal. So think about this. You can ask me, Ajahn, how about 5 million turns? Yes. Your tablet battery. Thank you. I have a charger. 2 seconds. Wait, where's my plug? Let's hope it doesn't break. If it breaks, then we may have a real holiday today. Okay. Is everyone good? Yes, you can. What about it? Right, the same rule apply to every step because the only condition for you to use a rule is that you start in white, which after the first turn, after your first turn, you end up in white, right? That is why you only need to prove the first turn, not the first turn, only one turn. Are we good? Right, because the second turn, you are starting at exactly the same condition, which is white. Okay, is everyone good? That we only need one turn before we get into the details of how exactly are we going to prove it, right? I want you to see the big picture, but you don't need to prove for like a million turns. You don't need to prove for all the possibility. All you need to do is make sure that after one turn, you end up exactly the same condition where you started, which is white, right? The second turn, if you look at it, it's the same thing. It's like self-repeating pattern, right? So far, so good. Any questions so far though on the big picture? This is the key. The key is one move. You don't really need to care about what you're going to do next. You only care about one exact move. Okay. Any questions though? Any question? This is important. Right. This is why it's called structure induction because when I draw it for you, right? I draw it for you like this. It's a line. Actually, there's another white over here, which go to another white, which may go back to that white, which may go back to the first white. Right? And then you ask me, Ajahn, what about the infinite number of turns that you, because you have a cycle now, right? That's why it's called structural induction because there is no order in it, but you spread around the condition that you have, the invariant that you have, the fact that you are white. Okay? That's why we only need one turn. And this is why I call it structural induction because there is no order like what we did last time, right? What we did last time, we have things ordered nicely, 1 to 2 to 3 to 4 to 5, right? And then we assume 4 to prove 5, but there's no 4 and 5 here. Okay, there's no 4 and 5 here. Any questions? So this is important point. Let me pause here like another 10 seconds before we actually gonna prove this. But the key is this guy, the one move. Okay. Okay, let me get rid of this and actually prove it. Right, proof invariant is to proving the invariant typically is structural induction. You're gonna see other example as well. This thing shows up in your code as well. So for example, you want to make sure that your invariant, if you write a code for a plane, your invariant is that the plane is not gonna go down. Right? You want to prove that that's true for every single second from now on, no matter how the pilot turned the plane or how the pilot kicked the plane. As long as it doesn't break, you want to prove that. Actually, that's a real job that you actually need to sign line by line. So for the code that run on embedded system, typically, so for the embedded system, like a plane, the one that has to do with people's life, or in the medical equipments, when you write the code, someone's gonna sign the signature next to it. Okay. So imagine you guys might have, one of you guys might end up in a job where you need to write a software for airplane. And are you sure that you want to write on that plane? Look at your friends. I don't know, you may not ever see your friend's face yet, but think about this. You may need to write on a plane where the code is written by your friend, and you want to be sure that you're not going to die that day. Right. Some condition that always hold true. So for example, the fact that x plus y is even always holds true. So you want to show that after one step, that thing still holds true. Okay, so let me write this. You want to show that it still end up in y. What that means that if you end up in x and y prime, you want to check that x prime plus y prime is even. Okay, so that's good. So this is what we're gonna do. What we're gonna do. So here are all the possible moves. Okay, here are all the possible moves. Okay, the bishop can only do 4 moves, right? There are only 4 types of moves. So there is a diagonally up, left, down, right, and over here, over there, and over there. Actually, the 2 are the same. So let me just write here. So diagonally like this, or diagonally like this. Okay, you can group them up any way you like. So this is move A and move B. Okay, here's where you start. Everyone get right? The bishop can only do 2 moves, so that means you only need to show that these 2 moves will end you up in white always. Okay, only after one turn. Actually, one turn might be a better word. Okay, so all these moves, right? You want to show that it end up you in white. So let's quantify this. What exactly do I mean? So what I mean is the following. This kind of move turns from your x and y. Let me write here, x and y into, right? So wait 2 seconds. X, okay, into x minus n and y plus n. Right? Because you go diagonally to, if you go left, then you go up in y. If you go more in x, you go less in y. Right? So far so good? And then good, right? So that means what you need to show, right? These are all your x prime and y prime. These are where you end up, right? After the move, this is your x prime and this is your y prime. How do you show that you still end up in even? How do you show that you still end up in even, right? For n, for some n in integer, could be negative as well. Right, you want to show that x plus y is still even, right? So x prime, what? plus y prime, we want to, so we hope it's even. Hope is even. Okay, so that means you just add them up, right? X prime plus y prime. We know from the above is x minus n plus y plus n. So that becomes x plus y. And how do I know that x plus y is even? How do I know that x plus y is even? Because we have it here. It's the starting point, right? Because we have it here. So let me call it's even, which is even. So we are done with the first move. Okay, that's good, right? So the proof is actually easy. The proof is actually quite obvious. You just try all the moves and you just show exactly the property that you need to show. Okay, so that's the first move is done. Are we good? Any questions or any questions? The first move is done. The second move is a little bit more complicated, but it's not that complicated. So the second move, it turns from x and y to what? Very good. Both plus n, x plus n and y plus n for some n in integer. Okay. So then this is your x prime and y prime. Let me write here. I need another color. Pink. X prime, and this is y prime. So you want to show that x prime plus y prime is even. What is it equal to? Well, you can add it, right? So these two guys, you can get x plus y plus 2n. How do you know this guy is even? How do you know that this guy is even? 2n is even and x plus y is even. Is even plus even, which is even. And then we're done, right? So then you know that this is always true. That since, what is n, sorry? N is because when you move a bishop, right? Let's say you start here. You can move here. That's plus one, right? You can move here, which is plus two. You can move here, which is plus three. So n is that number. Okay, we group them into two groups, but we have parameterized it inside as well. Are we good, Peter? So what we have shown, right? What we have shown, the formal proof is about the argument I made earlier that you only need one move is in the lecture note if you want to go read it. But I think you get the idea that you only need one move. The formal proof is in the lecture notes, but you get the idea, right? That you sort of spread things around. Okay, so we have shown that after one move, you're going to end up in exactly the same condition that you started with. You're going to have the same properties that you started with. Okay, which means, so only with this, you have proof that after any number of turns, right? Any number of turns, any number. Remember, we only show one, but it actually implies any number of turns. We always end up in white. Okay, so no green. Okay, so clear though, the example is quite simple in the proof, but the concept, the fact that you only need one turn, this is very important. Okay, think about this. This is like induction. When you do induction, you use your friend and you don't care what your friend does. So you actually did one step, but in that case, you know exactly the direction of what you're doing. No, green. Okay? So the idea that is important here is that you only need one step. You don't care what you do afterward. Okay? That's untrue. Yes. In this case, you are your friend. because you make sure that you end up in exactly the same condition that you started with, that you know how to do. Okay. Any question on this example though? Any question on this example? Okay. If not, let's do another one. Let's do another one. Any questions though? Any question? The key here is you only need one term. Okay. And that's actually not the hard part. The hard part is you're gonna see in here. Let me do it 8 by 8. Wait, I have a grid paper. 2 seconds. A grid paper, a page from template. A grid paper, engineering. Okay, good. I have an 8 by 8 grid. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. This is an 8 by 8 grid. Okay. So let me ask you this. Can you put the domino that looks like 2 by 1? Can you tile it in? What do you think? Yes, of course, it's clear, right? You tile it like it's quite clear to everyone that you can tile it. You can fill all the space in with this. Okay. Now 64, right? Now how about this? How about this? How about if I remove 2 pieces? Right? Removing 1, that's clear. You cannot do it because you end up with like odd numbers. But what about if I remove this one and this one? Can you do it? All right, try it on your paper and tell me. Try it on your paper. Yes, you still end up with even number right now, 62. But can you do it, right? But can you do it? No? Alexei said no. Are you sure? Two lines are not even. What about it? But they add up to even. Okay, so let's try. So let's try. You don't think so, right? You don't think so. Is it a Tetris? There used to be a Tetris problem. Maybe I'll put it in the homework. It's actually very cute. It's like 2-line answer, but it's actually very cute. I put it on midterm once. So you can try all you want. Actually, you cannot do it. Right? You can try it all you want. Then you're going to end up with something funny at the end. Like that one. Now I need to do this. Then you end up with this guy, which you cannot do it, right? Like these people, you cannot do it. Okay. So that means we want to show that you cannot tile it, right? After you try, you just can't do it. Don't even bother. We're gonna prove that we cannot do it. Okay, not tileable. Anyone know why? What actually prevents you from doing it? We have an even number of grid for 2 by 1, but you still cannot tile it. Okay. This actually goes back to a question someone asked on Discord that he shows that the number of grid is divisible by 2 or 3 and whatever, and that doesn't imply it's tileable. In this case also, it's not tileable. Same as bishop. What about bishop? What about bishop? What do you mean? Right? The way you tile? What about it? What about the way I tile? You can try it some other ways. Okay. So yes, the way I tile it, I only tile it horizontally or vertically. But what about it though? What about it? What about it? Let me help you. What about it? I want you to think along though. In this class, it's extremely important that you think along. You try to figure out the puzzle. That's very important part of the class. Learning what is a valid truth is totally different skill. The two missing are separate. Are you sure? But you can do this one, right? This one, I think it's clear for you that you can definitely do this one. If I take away these two, then you can, it's quite clear you can do it. Right? You did this. And you do this, and this, and this, and then you can fill the rest, right? So it's not that reason, so on, right? Something special about blocking it over here. Something very special about blocking it here. So let me paint the grid for you. Maybe you see something. Let me paint the grid. Maybe you see something. 2 seconds. You type in a lot, but I need. Okay. The odd row doesn't add up. It doesn't pair up. The line missing is odd. We cannot fit because the missing place vertically. Good. Now what? Notice something, right? Now what? Notice something that whenever we place it, whenever we place a tile, it's always one red and one white. Right? No matter how you do it, it's gonna be one red and one white. Right? It's gonna be one red and one white. Is it similar to a card game we play? I don't know. What card game did we play? No, not similar, not similar. The card trick that you did as a homework, right? No. Actually, I need a card today. Second. We're gonna learn how to scam people today. 2 seconds. Okay. Okay, let's do this one real quick and then we're gonna learn how to scam people. Actually, this trick gonna work like forever. This trick gonna work for so many people. Okay, what about this? What about it? Okay, so now what says something very important, right? That when we place it, we place it on one white and one red. But what about it that prevents us from placing the whole thing? We don't have enough red and white pair. So good. So that means what we need to keep track, right? What we need to keep track. What we need to keep track is the number of red and white that's left on the screen, right? So this is the number that we keep track. So this, think about this. The technical term is called the state. Okay, it's like the state is like the where the bishop is, the state of the game that you can summarize it. The state of the game is going to be the number of red and the number of white that's left. What about it that you want to show? What's the final state though? What's the final state that you want to be? If every claim that is tileable, what does it mean if tileable? Okay, that means it has to be 0, right? All the red and white has to be used. Okay, so far so good. Seven good. So this is our hope, which you cannot reach it, right? We cannot do it. But this is our hope. If we can do, if we can reach 0, 0, then we are done. But we're gonna prove that we cannot. Okay, so let's look at the start state. How many red and how many blacks? How many red and how many white? Sorry. How many reds are there? 30? No. You take out the corner, right? That corner is banned. That, oh well, and I banned it with red, which I should not do. 2 seconds. That corner is banned. So how many reds and how many whites exactly? Good. There are 32 red and 30 white. 32 and 30. Okay. So that's good. So after each turn, After each turn, what exactly did we do to red and white? Each turn that we place down the dominoes. But let me pause here. Is everyone good with 32 and 30? Right? Because initially they are 32 each, but then I take away 2 whites at the corners. Right? So, good. Each turn, right? Each turn. This is what we do. This is not a formal proof. We're gonna write a formal proof later, but you should sketch it. You take red and white, okay? And then you turn it into R minus 1 and W minus 1. This is every turn. This is what you're doing. Okay? So far, so good. Think about this. Think about this. We want to show that by doing this, this is like the only kind of turn you have, right? You want to show that by doing this, you are preserving something, some properties, like the fact that you end up in white, as in the bishop case, right? You want to show that this thing preserves something. What exactly does it preserve, though, that actually prevent this from happening? What is it? What does it preserve? This is typically the hard part of figuring out the invariant proof, though, is to figure out what to prove. That's the hard part. Proving is easy, but figure out what to prove that is meaningful is the hard part. That's why homework 4, you're going to do this in homework 4. Homework 4 has the least number of problems in that homework, but it's going to take you the longest. And actually, when you write a solution, it's actually the shortest as well. Figuring out what to prove is very important. So the question here that I have for you is, what exactly does it preserve that prevents 3230 to go down to 0, 0? Some property of it, something that you can check whether it's true or false easily. Not true though. I want something better though. No, what you said is entirely true, and you can do that. The amount we subtract by. What do you mean, Justin? What exactly do you mean? What do you mean? The amount we subtracted by. But you're close though. You have the keyword. You have the keyword. Except I don't know what you meant. We always recommend R and W by 1, but that doesn't prevent this from happening, right? That has nothing to do with the last one, right? So for example, you can say that the invariant is, I don't know, the sun rise on the east, but it has nothing to do with the state that you're talking about. To R left cannot combine. Okay, so what exactly is the invariant? Think about this. The invariant here is like last time. You want to show that x plus y is even, right? That's something you can show. You can always show that. What exactly do we want to show here? What exactly do you want to show here? Very good, Karit. That's excellent, but I'm going to move it a little bit though. Okay, Karit suggests that no matter how you do it, the thing that is preserved is R minus W is 2. Are we good? Not 0 though, but 2. Because you start in the state where R minus W is 2, and you subtract each one by 1, you can actually show that whatever you do, that R minus W is 2. No matter how you do it, no matter how you place it, right? R minus W is going to be 2, and that state, that state at the end, do not hold this property. Therefore, this thing, the technical term, is not reachable. Okay. Someone good though. The idea here is this guy. The idea here is what Karit was just saying. That R minus W is 2 is the invariant that you want to prove. Actually, what said earlier is also correct, except I was looking for this one. We good? So that means all we need to do is to show that after each turn, one turn, R minus W is preserved. If you start with the state where R minus W is 2, after one turn, R minus W is also 2, then you have the problem that you had before, that you are your friend, right? Because you end up in exactly the same state that you started with. Is that one good though, before we go write a proof? The goal here is to show that this move preserve that property. Okay. Is that one good? Any questions so far or any questions so far before we write on a formal proof? After we write a formal proof, then we're gonna take a short break because computer broke so much today. And then we're gonna learn how to scam people. Any questions? No, 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 no. Okay, so let's do this. I need a new page. Come on, internet. Wait a second. Okay, now that works. Okay, so the theorem is the following. Okay, you can just write this. R minus W is 2 is invariant. Okay, which is the same statement which is the same statement as no matter how many turns you play, you're gonna end up with state where R minus W is is true. Okay, so here's what we're gonna do. The proof. Let's assume we start in a state R and W where R minus W is 2. Okay. We want to show. What do we want to show? Can someone tell me? What do we want to show? Can someone tell me? What do we want to show? We start in the state of R and W where R minus W is 2. What do we want to show? Very good. After one turn, not every turn though. This is important. After one turn, R prime minus W prime is also 2. Are we good? Right. This is why we end up. We end up. Let me make a note here. We end up in R prime and W prime. This is just for formality, but you get the idea. Okay. So that means you can just list all the possible move, which is there's only one possible move. Okay. Place a domino. Let me write this. Place a domino. Okay. So that turns R and W into R minus 1 and W minus 1 that we agree upon. That's okay. So what do we need to check? What do we need to check? Let me make a note. What do we need to check? Someone. Oh, no, what said that already, right? We need to check that these two numbers, right? R prime and W prime, that the R prime minus W prime is also true. It's also 2, not true. We need to check R prime minus W prime, which is R minus 1, right? Minus W minus 1, which is exactly R minus W. And how do I know that it's 2? How do I know it's 2? Because of the thing that you assume you started with, right? We start in the R minus W where R minus W is 2. So this thing is equal to 2. As simple as that, right? You see, the proof is nothing but the hard part that requires a whole bunch of imagination that cannot exactly be taught is this. Okay, then you're done. Then you can include here. So that's okay. R minus W equals 2 is an invariant. Right? AKA, you can write this as well after any number of turns. Okay. Someone good with this proof though? Any question? Any questions? Any questions though for this proof? Any questions? Or it's clear, right? So let me write. And also, so this is time with the proof, and then you have the corollary, like corollary. This is like the follow-up, right? Because the thing that you really want to show that is this guy, the fact that it's not tileable, right? Corollary 0, 0 is not reachable. Because it since 0 minus 0 is 0, not equal to 2, thus not tileable. Thus it is not tileable. Seven good, right? So we get to what we need. Any questions so far though? Any questions so far? I want to point out that proving invariant is actually easy, but figuring out what to prove, this slide that Karik told me, that would take you a day, and proving this is going to take you like 5 minutes. Okay. Proving the invariant is easy because you just try all the moves and show that it's satisfying the invariant. Okay, but figuring out what to prove is hard. Any questions so far though? This is a basic question. You will see, and you'll love the circle. Wait 2 weeks, wait 2 weeks. This is homework 4, by the way. All these gonna be in your homework 4. These are gonna be in your homework 4. Corollary is so fancy. You can say follow up. It works too. I'm not even sure if I spelled it right. You have Grammarly with you, right? And Google to fix. Is it RY or I don't know. Go figure out how to spell this. I'm not even sure I spelled it correctly. Any questions though? If not, we're gonna take a 10 minutes break and you come back at 15:10. 15:10, okay? Come back then. And what he needs is on Discord. You know, I just restarted my computer. Discord is not up yet. Can you show the first page of the notes? Yes, I can. Oh, you need this, right? For problem 6. Say starting. I'm reading it and I don't get what you're trying to do. Wait 2 seconds. Let me try to read it. You actually don't need induction for that. So Keith, what you sent me on Discord is a no. The green part is that has nothing to do with the problem. The green part has nothing to do with the problem. The blue part is the one that I asked you to do. Homework too generally doesn't require strong induction. The green part is wrong though. The green part has something to do with the question, not that it's wrong, but it has nothing to do with the question. Right. Let me give you one more hint. Let's give you one more hint. You guys seem desperate. I claim the following. Okay, right? Your goal is to show this. This is actually the hard part. The other one are exactly the same thing. It's less than, this is your goal, right? This is you don't know yet, right? My hint is to show that this thing is less than something that you kind of know, which is you know that is less than that equal to 3 to the k. Wait. The other way, right? You want to show this, that 3k squared is less than or equals to 3 to the k, right? You want to show that, let me write it the other way around, that might be better. Okay, you want to do this, you want to do the following, that 3 to the k is greater than or equal to something you know, which is also greater than or equal to 3k squared. Like that's like 2 steps. Find that something and fill out the red. Find that something. And then the other one is the same. It's the same idea. Okay, that's one you know, right? Even though you do that, you still need the last piece, right? Even though you feel this is like k to the third, right? You know this from the inductive hypothesis, right? You still need to fill out this part, why exactly that is, which is easy. That's the easy part. What? Let me read it. You might be correct, but I don't know what you're doing. But that's not approved, right, Saran? Someone sent me the thing on Discord. The guy with the sum 6i. Clever idea though, except what you show down below is proof by example. Right? It's Saran, right? So the guy with the sum of 6. No. So this is what you wrote. Wait 2 seconds. So this is what you wrote, right? This is actually a good idea, except I don't know where you're going with it. You wrote the following. Let me show other people as well. It's actually a very smart move. Right? You want to show this. You don't know it yet. You don't know it yet. You want to show that this thing is less than that guy. Right? So that means the left-hand side, you do some really smart move, which I don't know how to continue with that. Plus the sum of 6i, I equals 0 to k. And then less than or equal to 3 to the somehow that k, that plus 1 is gone. I don't know what you're doing, but k plus 1 is gone. But let's assume you have the plus 1. Because this thing is actually n plus 1 over 2. N minus 1 or n plus 1? N plus 1 or n minus 1? Maybe you need this. I think you need this. So if you do this, then it kind of works. And then there has to be plus 1 over here, but I don't know where you're going to go next. It's a smart move, except I don't know where to go from here. If you know where to go, like I said, you can produce the thing that I don't expect you to do, and as long as it's correct, then I'm good. As long as it's valid, your TA is going to read it. They are mathematicians, so they know what a proof is. It's actually kind of hard because you only know one thing, right? You only know this and 3 to the k. That's all you know from the inductive hypothesis. There are more than one ways to do this. I can think of another way, which you may not like, involving calculus. I don't know where you want to go next. Okay. Good idea though. Good idea with this. I have to read it and pause for like 15 seconds to figure out, okay, this is what you're trying to do. But I don't know where to go next. But the rest that you show in the table below, that's proof by example, doesn't work. Wait, 15:10 already. So let's do it. Let's do it. Let's learn how to scam people. 2 seconds. Or maybe I have a cooler example. Okay. Yes, we're gonna learn how to scam people. Can I see how you conclude the last theorem? Yes, I can show you. And remind me tonight to upload all the lectures and lecture notes before I forgot. I tend to forget a whole bunch of things. This is my like 8 meetings of the day. So the way I conclude the last theorem is the following. The goal is to show that 0, 0 is not reachable, right? It's to show you cannot pile it. That means you show that 0, 0 is not reachable because red minus black is not 2. Therefore, it's not reachable. So you cannot tile it. Okay. What is sim? What is sim? Which one? Oh, since, not sin. Sorry about that. It's the corner of iPad, so hard to write. Okay. So let's do this. Let me ask you some silly question. Some very silly question. Okay. You guys know about roulette, like roulette. Roulette. You bet on red and black. There's also green, but let's ignore the fact that they exist. You bet on red and black, and when you win, right? If you bet 1 baht, you get 2 baht back. That's like 1 and 2. Kind of makes sense, right? You have 2 choices, and each one of them is like 50-50. Okay, then you get 2 baht back. But if I show you this, how many reds and how many blacks are there? Let me switch the screen as well. I need the iPad. 2 seconds. Right, roulette is spinning the ball with that, spinning the little ball. 3 red and 2 blacks. If you want to bet, right? If you want to bet, which one would you bet though? If it's like, if you bet 1 baht, you get 2 baht back. You want to bet on the black. And today, I'm gonna let you do that. You're gonna bet on the black. So you are the house, essentially you are the house, and I'm the player, and I will always bet on red. That means since you are the house, right? You have 3 cards. Okay. Are we getting money today? No. No. And I can tell you without playing. I can tell you without playing. So here's how I'm gonna do it. Here's how I'm gonna do it. It's clear, right? That there's 3 black and 2 red. And 2 red. Okay. Time to scam us up. Yes, of course. What this class is all about, right? You can go back and tell your parents I pay the tuition for what? Scamming people, right? Wait, don't tell OEA though. They're gonna come after me. Don't tell OEA. They're gonna come after me. I teach people to scam people. Okay. Next term holiday. That would be nice though. That would be nice if I can get the whole term off to do something else. Okay, 3 black and 2 red. Here's how I'm gonna bet. Okay, so I promise the following. Bet on red, I'll bet on red. Okay? And here's how I'm gonna do it. The first turn, I'm gonna bet 6 baht. First turn, I'm gonna bet 16 baht. Okay, this is a rule. First turn, we're gonna bet 16 baht. And then, okay, and then I need to tell you how I would bet first, right? Otherwise, I cheat a little bit. And then, if I lose, I bet on red, still on red, right? 1.5 times the amount. If I win, I bet half the amount next turn. Okay, this game is gonna play like the following. I'm gonna bet on red. I'm gonna bet on red. Okay. Okay. I'm gonna bet on red always. And the first term gonna be 16 baht. Okay. The first turn is gonna be 16 baht. If let's say that the first turn we do this. Okay. I shuffle this. Let me make. There's only 5 cards. You can actually play it with 52, but it's too hard to handle. Okay. The first turn, I'm gonna open 1 card. If it's black, that means I lose, right? That means I lose. So I'm gonna lose all the 16 baht. Okay. So that means I'm gonna lose 16 baht. But the next turn, so 16 baht, if it come out black, if it's black, and right? If it's black, then I lose 16 baht. So I minus 16. But the next turn, I still bet on red, but I'm gonna bet 1.5, which is 24 baht. Okay. Someone good? Right? This is what I'm gonna do. I'm still gonna bet on red. This is on red. I always bet on red. Are we good? So if it comes out red, then I get my plus 16 baht, right? So I get 32 baht back, but I pay 16 baht earlier. So I get the profit of 16 baht. Actually here. Okay. So if I win, then I say that I'm gonna bet half the amount. So that means I'm gonna bet 8 baht, which is 16 times 0.5 on red as well. Okay. So far so good. That's how we're gonna play it. Okay, that's how we're gonna play it. And the way we play it, you're gonna shuffle it, right? You're gonna shuffle it. I don't know where the red and blacks are. And then we're gonna open one at a time. And once we open, we're gonna throw it away. And I tell you that I'm gonna always bet on red, no matter what. Right? And then this guy, you win again, and you open it one at a time, then I win the last 2 turns. Wait, this is hard to hold the camera. Okay. So far so good. This is what we're gonna do. This is what we're gonna do. Okay. So Everyone understand the game, right? Ish. So we shuffle the card and let me move my camera a bit. Again, please. Okay. So we have 5 cards, right? We have 5 cards. So each turn, right? The first turn, I'm gonna bet 16 baht. Okay. And I open it. If it's come out red, then I win. If it's come out black, then I lose the 16 baht. And then we play it again. I bet on the next turn with some specified amount. And then I open the card again. If it come out red, then I win. No, it didn't. So I lose again. And then I'm gonna bet on red the next turn as well. I lose again. Oh, that's a bad shuffle. Until I get the red. Keith, are we good? Let's do one example. Let's do one example. Maybe you're gonna get the idea. Let me switch the camera real quick. That's the ceiling. 2 seconds. Okay, but I need the notes though to show you. So here's what we're doing. Here's what we do. I shuffle the card. You can trust me on this one. Okay, I shuffle the cards, and that's the card. So let's do this. Let me write the table as well. So if win, then the next turn is going to be 1.5 times. Lose is going to be 0.5 times. Okay. So the first turn, this is turn 1. Turn 1, 2, 3, 4, 5. There's only 5 cards, right? So let me record the amount I win or lose. Okay. So I always bet red, the result, and the amount, win or lose, and then the bet that I made, right, and the profit slash loss. Okay. So here's what happened. The first turn I bet 16, right? That's the name of the game. I tell you this. Okay. Okay. And the first turn I bet 16. So we're gonna open the card. If it's come out red, I win. If it's come out black, you win. So it come out black, right? So that means what happens? This is black. So I'm gonna lose 16 baht. Okay, so far so good. So now you have 16 baht in your pocket. Okay. Then the next turn, because I lose, oops. Wait. I switched them. Win is 0.5 and lose is 1.5. So since I lose, right? Since I lose, I'm gonna bet 1.5 times that much. So the next turn I'm gonna bet 24 baht, 1.5 times 16. Okay, so far so good. And then we're gonna open another card, which is red. So that means I win, right? That means I win. So that means that's gonna be plus 24. Okay. Everyone good so far though? Everyone with me so far? Any questions so far about how we play the game? About how we play the game? Are we good so far though? And I think I have good feeling about this, right? That I'm gonna win, and I know exactly how I'm gonna win. I'm gonna win exactly 5 baht. I think that's about a good amount, right? Well, let's do this. Let's do this. Okay, open another card. Oops, I forgot to tell you how much I bet because I win, right? The next time I'm gonna bet half the amount, which is 12. Okay, and then I open it. That's a black. Okay, so what happens that I'm gonna lose 12 baht. Okay, so far so good. Because I lose, the next turn that I bet, that I'm gonna bet 1.5 times that amount, which is 18 baht. And the reason I pick 16 because it's guaranteed integers. Okay, so I have 18 baht. On this one, if it's red, then I win 18 baht. If it's black, then I lose 18 baht. So it's black, so that means I lose 18 baht. You see, I lose a whole bunch of money, right? So this thing is gonna be black, I lose. And to be fair, the last one, I'm gonna bet 1.5 times that amount, which is 27. Okay, 27 baht. And you know it has to come out red, right? Because there are two reds. So it come out red. So plus 27. Okay, everyone understand the game, right? Now, if you add that this all up, let's see. I win or I lose? What's it equal to though? Can someone help me? What's it equal to? The number is too much. Plus 5 baht, right? I win. Okay. So per second. Everyone understand the game, right? And I know that I'm gonna win 5 baht. What does that mean? What does that mean? Wait. I'm gonna win 5 baht. Now you say, Ajahn, you have to be cheating. You have to be cheating for sure, right? So here's what I'm gonna do. Instead of shuffling the card and open one at a time, okay, shuffling the card and open one at a time, that's boring. I'm just gonna let you pick the card and let me pick another black. That is not 4, so you can call it. Okay, let me pick the 2. Okay, let me change this to 2. Okay, so you can refer to which card you want to come up. I'm good, right? Now you can refer to which card you want it to come up. So let's do it again. Let's do it again, right? The game is 16 baht at the earlier. Always bet on red, and then I'm gonna bet 0.5 if win, 1.5 if lose. Okay, what do we do? So the first time, let's keep it till turn and result, bet and profit slash loss. Okay, so turn number 1, I bet 16 baht. That's the game, right? I bet 16 baht. Okay, you guys, tell me which one do you want, red or black? Do you want to win or do you want to lose? The first turn, what do you want? Do you want to win or do you want to lose? You want to win. Okay, I'm gonna give you the black one. I want to lose. Okay, let's trust risky this turn. Let's trust risky this turn. Okay, so you want to win. So I'm gonna lose 16 baht here. It's gonna be black. Okay, so second turn. Okay, risky pick the first turn. Now I'm gonna let Nawat pick the second turn. Nawat pick the second turn for me. You want to win or do you want to lose? Black or red? You want to lose, right? So you give me a red, right? Give me a red. Okay, so I say that since I lose, right, the next turn I'm gonna bet 1.5. Let me write this right. So I bet 24. Okay, and you say that it's a red, so that is a plus 24. Okay, third turn, keep pick one. Wait, I need to tell you how much I bet first. I need to bet 12, right? Because I win last time. So this is 0.5. Keith, tell me, do you want to win? You want black, right? You want black? Okay, so that's gonna be black. So that means I lose. I'm gonna lose 12 baht. Okay, so that means the next turn, 1.5. So that's gonna be 18. Okay, who else? Justin, tell me, what do you want, black or red? What do you want, black or red? Red. Okay, so that means I win 18 baht, right? And then I'm gonna bet next turn half that amount. The last one, you have no choice, right? It's a black. So I'm gonna lose 9 baht. Can you add that up for me? Right, you can guess it's 5 baht. You see what's going on, right? The question is why? Question is why. Are we good? Right? This is what we want to show. Okay. What do we need to show? What exactly do we need to show? How does it work? In the homework, I think in homework 4 or 5, you will need to show how to get the maximum profit. I can tell you 1.5 and 5 is not the maximum profit, but it's easiest to calculate in class. Because if you want to watch, there is a movie called 21. It's actually based on, and this is the movie of the week, though. Movie of the week. we recommend movie every week. So this week is 21. I think it's on Netflix. Okay. And also there is this one is not a movie. It's called Search for the. This is the keyword MIT Windfall. I think it's the people who actually takes exactly the same class you are doing right now. They do some graph theory magic to cheat on the lottery. Okay, now why does it work? How do we show that it works for like you kind of know by now, right? No matter how you shuffle this, it's gonna work the same way. No matter how you shuffle this. I think you believe by now. Right? So we want to show that no matter the starting state you are, you're gonna end up with 5 baht. Okay. So let me help you a little bit. This one is not so trivial. This is not so trivial. Okay, let's think about this. Okay, here's what we want to show. Okay, I want to show that every single combination, every single permutation of red and black, right? So you know you have a whole bunch of combination of red and black, right? The permutation of red and black, you can do this. You actually learn that it's 5 choose 2 after the midterm. But you know, there are a whole bunch of combinations of them. Right? If you have 52 cards, and that's a lot. Okay, so the question is, we want to show that all these permutations, right? And something B or B or B or something. And maybe in R looks alike, but you get the idea, right? That there are black and reds, and all these permutations, you want to make sure that all of these end up with 5 baht. This is all you want to show. Are we good? Right? The fact that I'm so confident that I'm going to win 5 baht is because of the following. That I know that every permutation, right? If I know that every permutation will end me up with a 5 baht, then yes, I'm good. So how do we want to show it though? Can anyone give me some good idea? How do we show it? At least we know certain combination, right? Give me 5 baht. We know which one. We know black, red, black, red, black, red, black, red. Oh, this one. We know this guy. We play this one. And we know it's 5 baht. Okay. We played that one already. It's 5 baht. Not really. This one doesn't involve so much mathematical formula, but you need to a little bit. Okay. We play this one, it's 5 baht, right? Case brute force. Actually, you can do it because it's 5 choose 2, right? There are like 5 factorial over 3 factorial, 2 factorial, which is what? About 15 cases or something? I don't know. Go figure it out. You can actually brute force, but think about this. Imagine that I play this with you with 52 cards, then you don't want to do the brute force. Okay. The order matters, right? The order matters. Like, so for example, these two games that we play, the thing that different is this three people, right? Black, red, black, and black, black, red. Okay, so anyone has a good idea though? Anyone has a good idea? How do we show that every one of them will gain 5 baht? Brute force works only in the small case. Or can we do something smarter? Can we do something smarter than brute force? Brute force is not bad though. Brute force is like what I'm doing every day. Like I'm too lazy to think that I brute force my way through. What do you think? What do you think? Any good idea? Any good idea? So the question here is, think about this. What we did in permutation, right? We want to show that if I move from, I don't know, from here to there, right? Think about this. All the permutation are sort of connected by to some sort of shuffling, right? I shuffle to get from one permutation to the other one. If I show that some simple move, okay, some simple move that get me from one permutation to the next, doesn't change the fact that I'm gonna use 5 baht, right? Some simple permutation, some simple move get me from one permutation to another one, right? If we know that there's some move that get me from one permutation to the next and it doesn't change 5 baht, then like everything gonna be 5 baht. Are we good? Right. Think about this. We know that this guy is 5 baht. Okay. And then the move that I show is a very simple move that gets me to everyone. So that means all my neighbors is going to be 5 baht. And then all the neighbors of neighbors of neighbors, right? All the neighbors of this neighbor is because we know the neighbors of neighbors is going to be 5 baht because it's exactly the same move. The blue move over here are exactly the same thing, right? And then the neighbors of the neighbor is going to be 5 baht, and eventually you're going to reach every single one of them. Everyone's going to be 5 baht, like COVID-19, right? If you're close to someone, then you get COVID. And once you get COVID, you spread it to other people. Okay. So this, you can call this COVID induction, works too. But the question is, what is that move? How do you change from one permutation to the next? The easiest way. Easiest way, what do you do? Just make sure you don't end up with the same. Shuffle is too hard. Now I suggest something easy. Switch the two. Right? If I switch 2 cards, let's say even adjacent one, doesn't matter, right? If I can switch the adjacent card, I can get from one permutation to the next. And if I show that if this move doesn't change the fact that I get 5 baht, then I'm really good, right? That means I can keep doing this. Like I can keep permutate. I can keep doing this. If switching to an adjacent card doesn't change the fact that I have 5 baht, then every permutation will give me 5 baht. That's really powerful, right? You only show one move and you get every single permutation. Are we good? So this is what we want to prove. We want to show. Oops. Exactly. That's why we proved the link, like what we did last time. What we did last time, we proved exactly one kind of link, except that's every link. Okay, we proved one link, except that is actually every link. Okay. So we want to show the theorem. Okay. Theorem. Every permutation give me 5 baht. Okay. I can actually write a smart contract to help you play this. There's a class on smart contract. I think next term or next term, taught by Ajahn Manal. I highly recommend you take it though. If you're interested, by Ajahn Manal. He is an expert. It's called blockchain technology or whatever it's called. He's a really nice person though. Go take class with him. A lot of people love him. Okay. It's either next term or next term. I don't remember which one. Maybe teach us to scam more. Actually, it's a special topic class, but it doesn't require much of the prerequisite. Check the prerequisite, but I don't think it's a lot. Maybe data structure is needed. That's all. I don't know. Don't take my word on it, but it's gonna be open sometime soon. Okay. And blockchain is like half of it is how to scam people, how to get greedy people to pay money. Yes, Ajahn Kritiya, Ajahn Gig will tell you what happens. You want to learn theory of computation? Good for you. That means you love Ajahn Kanat so much. Even I don't think I'll pass that course though. If I have to take the test now, it's hard, but you're going to be satisfied. Okay, what I wrote here is every permutation give me 5 baht. Permutation, or rearrangement, permutation. Okay, every permutation give me 5 baht. And what we're going to show, permutation, guys, permutation. If you want to sound like a mathematician, say permutation. No one else says it except mathematician. Every permutation give you 5 baht. Okay, so here's what we're going to prove, right? Assume we start on a permutation or a state that give me 5 baht. Okay, that give me 5 baht. And we want to show after a turn, that means after one card switch, I still get 5 baht. Okay. So that's good, right? Let me do this real quick because I start to run out of time. I talk too much. So there are 2 cases that you need to consider, right? The first case is if it's the same color, right? So for example, if it's something, and it's both black, and then you switch the 2 card, that's easy, right? You don't change anything. Okay. Also, if it's this and then it's the same color, then you don't change anything. Nothing to do. Are we good? So the only interesting card, the only interesting thing is the following, right? If it's a win then lose, this is like red and black, right? I win and lose versus the lose then win. Okay. This is your proof. You need to show this, right? You want to show these 2 guys are equivalent. Okay. And by equivalent, to show that still give you 5 baht is the following. You need to show that given it's the same bet, right? It's clearly the same bet because the card in front are the same. The same bet. Okay. You want to make sure 2 things, right? You want to make sure 2 things that switching card doesn't really matter. That the whole profit during these 2 turns in these 2 turns are the same. Okay. You want to show this. After you switch the 2 cards, the profit are exactly the same. Okay. And you want to show that after you win or lose the last time, the outgoing bet is the same. Right? You want to show A, the profit and loss are the same, and the B, that the outgoing bet are the same. Okay, so far so good. Everyone good so far, right? Any questions though? Right? If you can show A and B, then it's clear that like switching the card doesn't do anything. You still get 5 baht back. Any questions so far? Though? Any question? Then I'm gonna write a proof really quickly because it's simple. You just work through it, right? So case A. So let's prove B first. Prove B first. Let's prove B, right? That the outgoing bet are the same, right? If the incoming bet is the amount of bet, if the first time I win, right? So let me show this. The outgoing bet. Okay. Let's say the win and lose situation. So that means the outgoing bet, let me call that OB, if I win and lose. So that's going to be the incoming bet, right? The first bet that I did. And because I win, I'm going to bet the next turn I have. And then I lose, I'm going to bet that 1.5, right? So let me make that clear. So because I win and lose, right? So that means this turn is going to be B. Because I win, that turn is going to be 0.5B. And that turn is going to be 1.5B. 1.5 times 0.5. Okay. Is everyone good on how I calculate the outgoing bet for the win and lose? Okay. Okay. So then you can calculate exactly the same thing, right? For the other situation. Now you tell me. Now you tell me. What is it? Lose and win. What's it? So you have the. What is the outgoing bet for this case? So this is B. You lose. What do you bet this turn though? You lose. What do you bet this turn? 1.5 B. And the next turn, what you're gonna do is you're gonna bet half of that, right? Because you win times 1.5 B. So that means the outgoing bet is gonna be 0.5 times 1.5. Oops. 1.5 times 0.5, which is exactly the outgoing bet of the other one. Okay, at least we match the outgoing bet, right? We match the outgoing bet, these two people. Okay, any questions so far? Any question? Now, at least we know. You can actually make a variant. Even this one, I think it's going to work on a lot of people. A lot of people are going to be greedy. There are 4 blacks, then I'm going to bet on black. There are 3 blacks, right? Okay, so far so good on the outgoing bet. Okay, but we still need to do another thing, right? That the profit and loss during the 2 turns are the same. So that means we need to do this. Let's do the profit. Let's call that P, win and lose, right? Okay, let's look at this picture again. So we have win and lose, right? We bet this guy B, right? And then we win, we're gonna bet it what? 1.5, not 1.5, 0.5 B, right? And lose, then win, right? We're gonna bet this guy B, and then we're gonna bet this guy 1.5 B. Okay, this situation, what's the total win? How much do you win or lose the first turn? What happens the first turn? How much did you win? If you bet B and you win, how much did you win? How much do you win? B, right? That's how much you get this turn. You get plus B. And you lose this turn, so you minus 0.5 B. So minus 0.5 B. That's the total win. So that becomes 0.5 B. And then you want to show the other one. Okay? You lose how much the first turn? You lose B because you bet B, right? So minus B, and then you win the second turn plus 1.5 B. So that becomes 0.5 B, which is exactly the same thing that you had above, right? And then that means you're done, right? Because of the outgoing bet are the same and the total profit are the same. Thus, since switching the card Doesn't change. The outgoing bet. No, the amount. No, the profit during the two term. I can't always win 5 baht. Regardless of permutation. Someone get? Try it with your parents. I think it works. Okay, so because switching the two cards, let's say the two adjacent card. Doesn't change the outgoing bet, not the profit. I can always win 5 baht, right? You want to get the idea, right? If I do this, how much do I win? 5 baht. If I switch these two cards, how much do I win? Still 5 baht. If I switch these two cards, I still win 5 baht. Okay, so that's the game. I think this works on your parents. You can try. I'm pretty sure it works on everyone. The first time I see it, that's gonna work. This is from, I think this trick is, if I remember correctly, is from Martin Gardner. He called himself recreational mathematician, but he is really good. Martin Gardner. Right, if you watch Veritasium, right? Or something. Martingale is actually what I figured out when I was like 12 years old. I went to a casino in what's that called? Our neighbor Khmer in Cambodia. Maybe it's sometime that I'm old enough to get into the casino, and then I figure out, okay, this is what I should do, Martingale. And then I learn about and then I learned about like what not to do. Maybe not 12, I think it's 18 or 15 or something. Cambodia way back then doesn't have age limit. Okay, so for this one, I think the thing is, you can see that the invariant that we did today, the proof is actually very easy, regardless of the permutation, regardless. Okay, so the thing that you see today is that it's actually quite easy to prove, but figuring out what to prove is another thing, and you're gonna see this in homework 4. Okay, the next time, I'm not sure what I'm gonna teach yet. I could do some more invariant to get you used to the problem, or I could start a new topic. Let me decide. You're gonna see that on Tuesday. Let me decide. Can you say something after class? Yes, but okay. Any questions though? The homework gonna be due on Thursday. Any question? Homework 3 is, yes, most of them you're gonna need strong induction. Let me stop recording.